an integral is really about finding the area under the curve. So for example, if we're given a simple y equals x graph and we're trying to find the integral of it, it's essentially trying to find this area, the shaded region underneath of it. Now, similarly to finding a regular integral, which is the area under a curve, finding the volume of an integral or volume of rotation of regions around lines, you would first of all be given a region. So let's say this is the region bounded by these two different graphs or functions. And obviously you would have the shaded region, and typically you'd be asked to find the volume by spinning it around an axis or a specific line or function. So let's say in this case it would be the x-axis. You would get something that spins around such that it comes out and towards and back and under you, and it spins around this axis right here, forming a almost unique washer or disc shape depending on what the question is asking. Typically, the schema you would want to follow when doing these questions have actually 5 steps. Step 1 is you want to sketch the graph. Step 2, you want to draw the reflection line. Step 3 would be to draw the reflection itself. Step 4 is to draw the test figure. And step 5 would be to draw the skeleton outline of the integral itself. And obviously, eventually, you would want to solve the problem. All right, now let's try doing a test problem. The problem this question asks is to find the volume of region bounded by y equals root x, x equals 0, y equals 3, and that volume is revolved around the x-axis. So first of all, what we want to do is you want to sketch the graph. So obviously you have x equals 0 right here. Then you're given y equals 3, which would probably be around, let's say, here. And finally, you have the y equals root x graph. So probably goes something like this. And then following that, the next step would be to draw the reflection line. Obviously, the reflection line, as said here, is the x-axis, so that's the reflection line right here. And afterwards, what you want to do is draw the reflection. So as you can tell, if this is the shape, the reflection would look a little something like this. We got the reflection now, and you want to draw a test figure. So given that you have an outside and an inside, you want to draw like a inside first. So here's the inner ring, and then finally the outer ring. To help yourself understand the depth a little bit, you can add a little shading and depth to the ring itself such that you know what you're dealing with and what shape you're working with. And then finally, you want to write down the skeleton outline. So because this is almost like a sphere or a disc, what you want to do is, obviously it's pi times some sort of radius squared. And because it's, it's from pi to 9 because you can solve for it. If root x equals 3, which is this point right here, then x has to equal to 9. So now you know the limits. So to begin with, your volume equals pi from 0 to 9, and you want to set the skeleton outline. What you want to do is you want to subtract the outside from the inside. So if we start first, you have 3 minus 0, so that's the outside, squared, minus, now if you look, this is the inside, which is root x. So root x minus 0 squared. And obviously, to figure out what the dx is, you take your fingers and you try to pick it up. And you pick it up this way, and it's horizontal. So it would end up being dx. Now you have your skeleton outline. Now what you want to do is you just simply solve the integral itself. So you do the math. I think the biggest takeaway from this is to figure out what shape you're dealing with. So in this case, you're working with a washer or a ring, and the biggest thing was you want to subtract the big R from the small r, which was incredibly important to figure out essentially what big shape minus small shape you're working with. And here we have the answer. What if the axis that you're rotating around is different? So this time we'll be changing the axis from x equals 0, y equals 0 to y equals 3. So obviously, as you would want to do first is, once again, you set up the x and y axis, you sketch the graph, which we had from before. That's 3. That's the root x graph, and then obviously you have the graph here. But then let's say, because it asks you to rotate around x equals 3 and not the x-axis, so this time it'll be flipping upwards this way, resulting in a graph like this. And now you would have to find the reflection. We found it, and the test figure would actually now be a disk because there's no distance between the two, forming a disk itself. Again, you could draw a little depth to it, 3D, just to figure out what shape you're dealing with. And then finally, you have to write the skeleton outline. Because this time there's only one radius, that's all you have to work with. Once again, you start with pi. And because we know from the last problem it's 0 to 9 is what we're dealing with, we could stick with that. And essentially you want to figure out, because it's 3 is the new boundary that's set, so then you have to figure out the radius, so it's 3 minus root x squared dx. And from there, you just solve the integral itself. So as you can see, here you go, 27 pi over 2 is the answer. Once again, what you want to notice is you want to figure out what test shape you have. So you want to know if you're working with a washer or a disc, and then obviously you want to find the radius. In this case, you only have one radius, so you work with pi r squared, this being the r. In conclusion, I think what's really important is that you follow these 5 steps. First of all, you want to sketch the graph, find a reflection line, draw the reflection, and then a 3D test figure, preferably one that sticks out to you so that you kind of get a better image of what you're dealing with. And then the skeleton outline, typically in pi r squared form. And particularly if you do have a washer, you want to get a big R minus small r for the actual radius. And that's it. That's how you find the area and volume using integrals, and in this case specifically volumes.